Swayam Prabha. Digital India. Educated India.
Let us move on to the next problem. So this question was asked in December 2014. The major product formed in the following reaction is. Here we have a hydroxy dicarboxylic acid is given, and this is treated with the DMP reagent and paratoluene sulfonic acid as a catalyst, and followed by the next step we treat the same intermediate or whatever the product that is obtained with the borane THF followed by acidic hydrolysis. So these are all the three different steps that are actually happening or being done to this particular dicarboxylic acid, and we end up with the four different options A, B, C and D. We have to identify what are the final product that will be formed. So if you look at the first reagent, the DMP, so the DMP generally protects hydroxy units, and that means one of the carboxylic acid and the hydroxyl unit may be protected. Then we end up with a one free carboxylic acid. Whether this is the one which will undergo reaction or this one will undergo reaction, that we will see later. So one of the hydroxy is protected, I mean there is only one hydroxy, so that is protected. One of the carboxylic acid is also protected, so we are left with only one reactive carboxylic acid that when treated with borane actually undergoes reduction to give a primary hydroxyl, and during the acidic workup what will happen is that primary hydroxyl may internally attack or maybe open up some of the intermediate that is formed. Then we end up with the final product. So this is the overall reactions what could be possible, and based on that we have to see what are all the reactions A, B, C, D. All the cases, if you very carefully look at, they all have a hydroxy unit and the lactone. So in other words, we have a lactone and we also have the hydroxy unit. So it's very difficult to judge without actually working out the mechanism what could be the final product in this particular case. So let us work through this particular reagents and the reactions. So the first one is we have the alpha hydroxy acid, and this is protected as a lactone by 2,2-dimethoxypropane or the DMP. So this is the first step that happens. So this hydroxyl and this carboxylic acids OH both are actually protected, and then the next step is reaction with the borane. So we already know borane reaction reduces the carboxylic acid to primary hydroxyl unit. So this is what actually happens, and the last step is reaction with the acidic reagent H3O+. So when we have H3O+, that is the acidic condition. So under this acidic conditions, this hydrogen may coordinate with the lactone carbonyl. So once it coordinates with the lactone carbonyl, this carbonyl carbon becomes delta positive. So once the carbonyl carbon becomes delta positive, a lone pair of electron from the hydroxy oxygen can hit this carbonyl carbon, and that will open up this lactone moiety, and which in turn can undergo loss of this particular unit. So we end up with the final product as shown here. This is completely lost, and we end up with a lactone. This oxygen becomes the hydroxy unit as shown here, and this OH forms the lactone ring, and this particular alcohol, this oxygen, is lost as a leaving group. So that is how we can actually end up with from one lactone to another lactone will be formed with the loss of this particular unit. So this overall reaction actually is conversion of a dicarboxylic acid into a hydroxylactone. So let us move on to the next problem. So here the correct sequence of steps involved in the following transformation is. This question was asked in December 2017. So we have a carbonyl compound that is reacted with the alpha beta unsaturated compound to give a phenolic derivative. So this is the overall reaction. So what are all the steps that will be involved in this particular reaction is Michael addition reaction, aldol condensation, syn elimination, keto-enol tautomerism. So these are all the various reactions that are given. And the next one is aldol condensation, electrocyclic ring closing, syn elimination and dehydrogenation. Then again Michael addition, Claisen condensation, anti-elimination and keto-enol tautomerization. The last one is Robinson annihilation sequence, dehydrogenation and anti-elimination. So by looking at these reactions, we can easily figure it out in the starting material or in the final this reagent. We do not have a ester unit. So Claisen condensation is basically a ester condensation reaction. So we can easily figure it out. C is not the right choice because that involves Claisen condensation and we do not have a substrate for a Claisen condensation. So that is ruled out. And then we have other reactions. If you look at Robinson annihilation sequence, Robinson annihilation sequence is nothing but the Michael addition and aldol condensation combination only. So that means we have two reactions which are very similar to each other. The only difference is the one of the first condition talks about the syn elimination, the other one talks about dehydrogenation. If we look at very carefully, when there is a dehydrogenation, that means aromatization. So that may not be a required product because we have a phenolic derivative as our final product. So that means dehydrogenation may not be the right reaction because dehydrogenation removes the double bond, but our final product has a double bond. So if you logically apply, then this dehydrogenation reaction may not also be the right choice. So that also we can rule out. And then we are end up with only two reactions, the first two, A and B. But if you very carefully look at AB, the B reaction does not have a Michael addition. So that means it is kind of a difficult one to say whether it could be the possible reaction or not, is quite questionable. But what we can assume that is A may be the most appropriate reaction because if you look at this is a substrate which can easily undergo Michael addition reaction. And we also have the corresponding units which are required for the Michael addition reaction. So this as a 1,4 addition is possible on this particular substrate. So the reaction which is most probably can happen is a Michael addition. So that means A may be more or less the required product. How do we actually know that is? Let us carry out the reactions as shown here and then we will find it out whether we end up with a phenolic derivative or not. Then we can exactly say yes, that is the right option for this one. So here are all the various reactions that are possible is given here. Michael addition is nothing but the 1,4 addition reaction. Aldol condensation is generally in this particular case, if the aldol condensation is carried out in the presence of a base, will be followed by dehydration. Dehydration means we are actually producing a alkene. A double bond will be made or produced in that particular reaction. So in other words, our final product has a double bond. So this may be possible in such a way that if an aldol reaction happens followed by dehydration, so we are introducing an alkene or a double bond is being introduced. Then syn elimination, if you talk about syn elimination, also introduces a double bond. So that means these are actually giving a hint to us, okay, this is the right direction you have to go to identify what is the final product. And then the final one is again keto-enol tautomer. So what is keto-enol tautomer? Ketone group is having a, this is a ketone group that undergoes enol tautomer. So enol has a required unit. So we have some enolic derivative that is present here. So in other words, all these reactions, see Michael addition followed by aldol condensation leads to a double bond. So one double bond may be introduced that way. Syn elimination, another double bond is introduced. Keto-enol tautomerism, third double bond is introduced. In other words, we have three double bonds in the molecule and all the three can be possible using this particular combination. So we can assume that the option A is the right combination of reactions. Let us look at how the reactions will actually proceed. And the only thing is, if we talk about a basic condition, that is how the reaction actually initiated. So the first step is the Michael addition. So the Michael addition, this particular unit gets added here to this particular carbon, and we end up with the Michael addition product. So you already know the simple mechanism for this Michael addition, so that's the reason I am not explaining it here elaborately. So basically the reaction is called as 1,4 addition, but actually the groups are added, that is the nucleophile and the hydrogen are added between carbon number 1 and 2. So this is what is basically the, because we end up with the enol derivative undergoes ketoenol tautomers to give the carbonyl compound. So this carbonyl group is actually obtained after the 1,4 addition happens. So that is where we say this carbon and this carbon are the two places where the two groups nucleophile, this is the nucleophile that is being added here, and this is the hydrogen that is added. So that way we say it is actually ending up with a 1,2 product, but the overall reaction is basically called as 1,4 addition reaction. And the next step is the aldol condensation. So the aldol condensation generates the carbanion here, and this undergoes a intramolecular addition reaction to give the hydroxy derivative. And as we know, in the presence of a base, this can easily undergo elimination, that is loss of water is always possible in this particular case. So when the hydrogen is present here, this will be moved to here and the hydroxy group is lost, which leads to the introduction of the first double bond, that is what is required. And then our next step is the thin elimination. So the thin elimination happens at the top here. The sulfonyl group is actually lost in this particular case. So the thin elimination leads to the introduction of the second double bond. And then finally what we end up is only the ketoenol tautomers. So this carbonyl group undergoes the ketoenol tautomer to give the corresponding hydroxy enol unit. So that way the number of or the sequence of reactions are Michael addition followed by aldol reaction followed by syn elimination, and the ketoenol tautomerism is the right set of reactions that will convert this compound to the corresponding phenolic derivative. We move on to the next problem. So the major product formed in the following reaction sequences, A, B, C, D, both 4 different products are actually given here, and this question was asked in December 2017. So we have a trihydric alcohol is given, and this is treated with acidic conditions in the presence of methanol followed by TBSCl, otherwise TBDMSCl in the presence of triethylamine as a base. Then PDC, which is generally used for the oxidation of the hydroxy units, and the last one is acetic acid and water. This is generally used for maybe some protection or deprotection. Let us see what are the reactions that are possible. So in the first step, acid and methanol is given. When we have acid and methanol, generally what is the most probable reaction is a ether formation. So that is, we can assume that acid and methanol in the presence of another alcohol leads to the formation of an ether. So the first one is the ether formation, and then the next reaction is TBSCl. So TBSCl generally protects the hydroxyl. So the next one will be TBS ether. One of the hydroxyl will be protected as TBS ether. And then PDC. PDC is generally used for the oxidation of one of the other hydroxyl. So we end up with a ketone unit. And then finally acetic acid and water condition generally cleaves the ether. So in other words, we will end up with an alcohol. So if we look at the combination, the ether is there in the beginning, but ether is not there in the end. So we can rule out this one. So these 3 are the functionalities that are supposed to be present in the molecule, and let us look at which are all the products that has this one. TBS ether should be there. Yes, we have TBS ether 1, 2, 3, 4. All the 4 has the TBS ether, and the carbonyl unit is there. So here I don't know whether we have a carbonyl. We have a carboxylic acid, because PDC does not give carboxylic acid. PDC only oxidizes a secondary hydroxyl to the ketone. It does not oxidize primary hydroxyl to the carboxylic acid. and that means this one is a questionable one. Let us keep it that way. And here we have a carbonyl unit, and here we have an aldehydic unit. Here we have a 2 carbonyl and an aldehydic unit. Maybe all the 3 combinations may be possible. Let us keep it that way. And the second one, we have to have the hydroxy unit in the final product. So if you look at here, we do not have a hydroxy unit because the ether that is formed in the first step is actually deprotected in the final step. So we have to have the hydroxyl. So in other words, C is completely ruled out, and maybe B and D are having similar things. B has the ketone, D has the aldehyde. So in other words, here also we can assume that, because if you are going to use a TBDMSCl, the TBDMSCl generally protects the primary hydroxyl in the presence of secondary hydroxyl. So in other words, this is the one which is protected as the primary hydroxyl, and this is the secondary hydroxyl is protected in D. So in other words, this may not be the right choice, because TBDMS protection happens on the primary hydroxyl very effectively, and that is the most important reaction that is happening. So in other words, B could be a logical product that we can actually assume by ruling out what are all the other possibilities that may not happen. So based on that, let us work out this and find it out whether B is our final product or not. So we have the starting triol. This, when treated with the methanol, undergoes the ether formation. So the various steps that are involved in the ether formation are actually given here. So we end up with the ether. How this reaction actually proceeds is, the most important thing is the neighboring group participation. So this carbocation can be easily stabilized by the presence of the neighboring oxygen. So this is the driving force for this particular reaction, and that leads to the formation of our ether. So this anomeric hydroxyl, if you look at carbohydrate chemistry, this anomeric hydroxyl is highly activated because of the presence of the neighboring oxygen unit, and the same thing happens here also. And the next step is, we have a primary hydroxyl and a secondary hydroxyl. Obviously we know primary hydroxyl undergoes reaction faster compared to the secondary hydroxyl for the TBDMS protection. So this is the second step that is happening, and finally we are going to do the oxidation using PDC. Now the secondary hydroxyl is the only thing that is left out. The one of the hydroxyl is protected as a methyl ether, another one is protected as the TBDMS or the silyl ether, and the only thing which is left unaffected is the secondary hydroxyl that undergoes oxidation by PDC to give the corresponding ketone, and the final step is reaction with acetic acid that deblocks or deprotects the methyl ether, and we end up with a hydroxide derivative. So this is the one we have actually assumed to be the right product, and actually by doing this reaction we also confirm that yes, that is the right product that is formed in this reaction.